Hello students, in this video we'll discuss three important results that pertain to adding positive fractions together. Here's our first result. Again, these are all very simple and they follow from the definition of addition. The proposition is that a over b plus c over b is equal to ab, a plus c, over b. Now, this is a lot different than our definition of addition, but that says if the denominators are the same, then you can just simply add the numerators together. That gives us an idea of this common denominator idea. So let's prove this. So the proof is we know that a over b plus c over b by definition of addition is equal to what? By definition of addition is equal to ab plus what? Plus bc over b times b. Now I can use the distributive property of multiplication to write the numerator as what? I can write the numerator as ab plus cb over b times b. And now I can write this as what? I can write this as a plus c times b over b times b. And now we're almost ready to, we're very tempted to cancel out yet, but what we need is we need one sort of final, sort of intermediate step to this. And so what I'm going to do is I'm going to state this as a lemma. And so my lemma states what? My lemma states that if I have a over b, then a over b is equivalent to a times c over b times c. In other words, I have a notion of equivalence for these things. And the proof of this lemma is straightforward. The proof of this lemma is that, well, I have that a times b times c is that equal to b times a times c. Well, yes it is, because I can write this over here as what? I can write this as b times a times c. We can actually sort of use the exact properties now. I can associate, then I can commute, then I have a times b times c, and finally I can write this as a times b times c by associating again. So in fact, this a over b is equivalent to a times c over b times c. So if there's a common factor on the top and the bottom, I can say that this is over here is exactly equivalent to a plus c over b. And I'm going to be a little bit liberal with my use of equals and sign. What I really mean by this is I really mean that these fractions are equivalent to each other. So in other words, a over b plus c over b is equivalent to a plus c over b, right? Sometimes when we begin to see the structure of how the natural numbers and the positive rational and the positive fractions are constructed, we sort of slip into our old notation with ease. All right, now the next property are order properties. Here's the next property. The property is that if a over b is bigger than c over d, then a over b plus e over f is bigger than c over d plus e over f. Okay? So what we're going to, we can assume this over here. So how does our proof go in this proposition? Our proof is as follows. Our proof is that we can suppose that a times d is what? A times d is larger than b times c. That's what this statement means over here. And what I'd like to show is what is our goal in this proof. Our goal is to show that af plus be over bf is greater than what? Is greater than cf plus de over df, which of course is equivalent to what? Now we can write down what this notion is. This is going to be af plus be times df. Is this bigger than what? Is this bigger than cf plus de times bf? That's exactly what to show. And so now we can rewrite this over here. We can rewrite this, of course, as a, and then we'll have a d, and then an f, and then an f, plus b e d f. Is this bigger than b c f f plus d e DEBF. That's what we'd like to show over here. This is to show if we can show that relationship over here, then we can then we'll have our result. So now what do we have over here? So what we can say is I can take this inequality that we have over here and multiply both sides by 2f's. So I can say ADFF is bigger than BCFF. And that tells us that this term over here, this circled term, is bigger than this circled term. That's excellent. And now we need one more relationship over here. I have a, let's take a look over here. I have a B, and then E, and then a D, and an F. So my goal now is to show that BEDF is bigger than BDEF. Well, those two expressions over here are what? Are equal to each other. And so that's perfectly fine. So in other words, we have that BEDF, so BEDF is equal to BEDF. And so our conclusion from this simple statement over here is that ADFF plus BEDF is bigger than BCFF plus BEDF, and that is exactly equivalent to this statement over here, which is exactly what we want to show, and therefore we have our result. So in other words, if I have an inequality between two positive fractions, if I add another positive fraction to both sides of the inequality, the sense of the inequality is preserved. Thank you very much.